You can specify a vector like this in all sorts of ways. You see, as it is at the moment, just sort of sticking out into space like that, there's no real means of specifying it. There's no frame of reference. If I call that vector q, then what we're really after in this program is some means of communication, some means of telling somebody else just what that vector q is. And I can go some way towards that if I use this box, because you see, if I put that box over the vector like that, then I can identify the vector q with the diagonal of the box. To get to the end of the arrow, you see, I can go 8 units along this edge, and then 6 along this edge, and finally 4 up here, and that brings me to q. Now, most of the box which we superimposed onto the vector q is redundant. I used only 3 of its edges to specify q. So really, you see, I can forget about the box and just think about the route to q along these directions. Now, R3 is a bit complicated to show you, so what we're going to do is to first of all have a look at R2 to see what problems are involved and how to tackle them. So essentially, we're going to look at a vector like P here and discuss ways of specifying vectors like this. Now, remember, what we want to do is to end up with a way of specifying any vector in R2. So when I put up a vector like this, P, then P is really standing for any possible vector you might like to think of in R2. Well, the way we can tackle this one is to use 2 vectors like this. We can use a vector here, put that one on there, call that u, and another vector here, which I'm going to call v. And I can use these 2 vectors to specify the vector p. And the way I do it is this. If I scalar multiply the vector u by 2, then I just get a vector up there twice its length. That'll be the vector 2u. I'll do the similar thing to v. Scalar multiply the vector v by 3, and that'll give me a vector out there. And that one will be 3v. And these vectors, 2u and 3v, will in fact get me to p, because if I take a copy of 2u, you see, and push it up here, then what I get is this vector specifying the vector p. And of course, what is that vector? Well, it's just 2u plus 3v. In other words, p is 2u plus 3v. But remember, p can be any vector in R2 expressed as a linear combination of the 2 vectors u and v. Here, for example, p is 4u minus 4v. And here, p is minus 3u plus 4v. So u and v can be used to define any vector in R2. But what if u was used on its own? You see, it would only generate vectors parallel to itself. So all vectors generated are linearly dependent on u. And similarly, v on its own will only generate vectors which are linearly dependent on v. So u and v must be linearly independent to generate the whole of R2. What if we use an additional vector, w? Well, here's a vector p, and here's a linear combination of u, v, and w, which specifies p. And here's another. And another. But with u and v alone, the linear combination which specifies a particular vector p is unique. So in R2, 2 linearly independent vectors form a basis. But remember, we were talking originally about R3. Well, fortunately, we can use the same approach for R3 as we did for R2. We've just seen that in R2 we can take any two linearly independent vectors and they'll generate any other vector in the space. But two vectors such as x and y in R3 will not specify just any vector in R3. They will only specify a vector in the plane of x and y, such as this vector q, which is the linear combination 3x plus 4y. But to specify a vector q which is not in the plane of x and y, we need another vector. Call it z, also not in the plane of x and y. So the linear combination for this particular vector q is 6x plus 8y plus 4z. And the linear combination of x, y and z which specifies a vector q in R3 is unique. For example, neither this combination nor this one will specify q. It would seem that in the same way that we needed two independent vectors to form a basis in R2, in R3 we're going to need three independent vectors to form a basis. But then you see it comes down to actually testing to see when vectors are independent. We want to test whether vectors such as x and y are independent. We look for a linear combination of x and y which produces the zero vector. What values of alpha and beta would do this? Well, let's look at two dependent vectors, x and y. In fact, 2x minus y produces the zero vector. So we've been able to produce the zero vector with non-zero values of alpha and beta. Alpha equals 2 and beta equals minus 1. But we were interested in two independent vectors, x and y. Look at a vector r, which is a combination of x and y. The only way r becomes the zero vector for the independent vectors x and y is when both the coefficients alpha and beta are 0. So we look at this equation in alpha and beta, and then x and y are linearly independent only if alpha equals 0 and beta equals 0 are the only solutions. So this becomes our test then for linear independence. You've already met it in the text, and you can actually extend it to three vectors. If you wanted to test for the independence of x, y and z, then you just look at a linear combination producing the zero vector again, and then x, y and z will be linearly independent only if alpha is 0, beta is 0 and gamma is 0. And for linear independence, these must be the only solutions. And that's a test that we can now use in the example that we had before. We can go back and look at the vector q we had, and we can look at the three vectors we were using earlier to specify q, and actually test to see if they're independent. What we've done is to put a grid system here. It's quite arbitrary, of course, just like the box we used earlier. With this grid, the vector q is specified by the coordinates 0, 10, 4. And down here, we've got the three vectors x, y, and z. Here's x, the vector 4/5, 3/5, 0. Z up here, 0, 0, 1. And y is round the back here, minus 3/5, 4/5, 0. Well, now we've got these numbers here, we can actually use them to apply the test for linear independence that we just had to these three vectors x, y, and z. And what's more, once we've done that, we can actually calculate the linear combination of x, y, and z that we need to specify this vector q. And to do that for us, here's Robin.
Well, as Norman's just told you, I want to check that the vectors x, y, and z are linearly independent. And to save time, I've got the details already written out here. I start with a linear combination alpha x plus beta y plus gamma z equals 0. That's the zero vector. And I want to show that the numbers alpha, beta, and gamma are all 0. So we start by actually writing out the coordinates of x, y, and z. There's x, there's y, and there's z. And that's the 0 vector. If we now look at each coordinate in turn, then we get 3 simultaneous equations. These ones here. And these can be solved very easily to give us the solution alpha equals 0, beta equals 0, and gamma equals 0. And that's the only possible solution. Well, I did another calculation before the program started. And that was to find the vector q as a linear combination of x, y, and z. We want to write alpha x plus beta y plus gamma z equals q, and we want to find the values of alpha, beta, and gamma. We start just as before, putting in the coordinates of x, y, and z, and also of q, and that leads, just as before, to 3 simultaneous equations. These are then solved after a bit of work, and that gives alpha equals 6, beta equals 8, and gamma equals 4. And again, those are the only solutions. So the only way in which this top equation can hold is for those values of alpha, beta, and gamma that we've just said. In other words, that q is 6x plus 8y plus 4z. Well, none of that was particularly difficult, but it can get very tedious, especially if the simultaneous equations that we end up with are at all complicated. And what would be really useful is if we could find some method for doing problems like this which don't involve the solution of lots of simultaneous equations. Unfortunately, in this case, there is a method that we can use, and it depends on the fact that x, y, and z form an orthogonal basis. Well, in R2 and R3, vectors are said to be orthogonal if they're at right angles. And it should be pretty clear that if you've got vectors at right angles, they can't possibly be linearly dependent. But it certainly makes things very much easier for us because it's far easier to test for whether vectors are orthogonal than it is to solve a set of simultaneous equations. So to test whether a set of orthogonal vectors forms a basis, if we've got the right number of them, then they must do. For example, the vectors that we had before, x, y, and z. It's not difficult to check that they're orthogonal. We'll be doing that in a minute. And there are 3 of them, so they must form a basis for R3. So all we need now is a test for when 2 vectors are orthogonal. To test for orthogonality, we use the dot product of 2 vectors. X and y are any 2 vectors, and the dot product is the length of y times the projection of x onto y. In this example, the length of x is 2, and the length of y is 3, so that in this case, x dot y is about 5.2. Now look at how the dot product changes as the angle between x and y changes. And notice how the projection of x onto y gets smaller. And when x and y are at right angles, this projection of x onto y is 0. So x dot y is 0. So when x and y are at right angles, their dot product is 0. Well, we can actually take this as our definition of orthogonality. We say that 2 vectors are orthogonal if their dot product is 0. Well, let's try out this definition with a couple of examples. I'm going to take 2 vectors in R3, say 1, 2, 3, and 0, 1, 2. And I'm going to form their dot product. Well, how do we do that? We do it just as in R2. We take the first coordinate and multiply them. We take the second coordinates and multiply them. We take the third coordinates and multiply them. And we just add the results. So what do we get in this case? We get 1 times 0, which is 0, plus 2 times 1, which is 2, plus 3 times 2, which is 6, and adding these gives 8, which is certainly not 0. So these are not orthogonal. Let's now try it with two vectors that we know are orthogonal. Let's take the vectors x and y and form their dot product. Well, x is 4/5, 3/5, 0, and y is minus 3/5, 4/5, 0, and we do the calculation just as before. This times this is minus 12 over 25 plus 3/5 times 4/5, that's plus 12 over 25 plus 0 times 0, that's just 0, and adding these up gives us 0. So, in other words, x and y are orthogonal. And you might like to try it for yourself to check that x and z are orthogonal and that y and z are orthogonal. It's a simple exercise we can try after the program. And what that tells us is that x, y and z are all orthogonal, and so they form an orthogonal basis.
But how do we know that two orthogonal vectors are linearly independent? Well, we've already seen that really geometrically. You'll find a detailed algebraic proof in the text. Three orthogonal vectors are also independent. One advantage of using orthogonal vectors is that if you have the right number, then you have a basis. You remember when Robin was trying to work out the linear combination of x, y and z, which specified the particular vector q? He had some rather tedious simultaneous equations to tackle, if you remember. Well, now he can approach the same problem, trying to specify the vector q in terms of x, y and z, but this time exploiting the fact that x, y and z form an orthogonal basis.
So I want to find the linear combination of x, y and z that gives me the vector q. It's the problem I did earlier in the program, except that this time I want to solve it using orthogonality. Well, I've got the equation written up here, and the first thing I want to do is to dot this equation with the vector x. I take x dot the left-hand side, and that's equal to x dot q. The next step is to take this left-hand side and break it up into three separate terms. So the first term is alpha into x dot x. Plus beta into x dot y. Plus gamma into x dot z. And that's equal to x dot q. Well, this all looks rather complicated, but it simplifies a lot as soon as you remember that the vectors x, y and z are all orthogonal. Because x and y are orthogonal, and so their dot product is 0. That term just disappears. And x and z are orthogonal, so that term disappears as well. And what are we left with? We're left with, on the left-hand side, alpha x dot x equals, on the right-hand side, x dot q. So if we want to calculate alpha, we don't have to solve any simultaneous equations this time. We just have to calculate a couple of dot products. And you might like to try this later on. If you work out x dot x, you'll find, in fact, that it turns out to be just 1. So alpha is equal to x dot q, and you can calculate that as well. That just turns out to be 6. Well, it's very convenient that x dot x was equal to 1 because it meant that we could calculate alpha straight away as x dot q. But the fact that x dot x was equal to 1 was not coincidence. We actually fixed it that way. And if you calculate y dot y and z dot z, you'll find that they both come to 1 as well. So the vectors x, y, and z have the property not only that they're orthogonal, but that if you take the dot product of each with itself, it's just 1. And what that means in fact is that the length of each of those vectors is 1. Well, bases of this kind, x, y, and z, which have the property that they're orthogonal and each vector is of length 1, are so important that we give them a special name. We call them orthonormal bases. So an orthonormal basis is a basis in which the vectors are orthogonal and each vector in it has length 1. Well, now let's get back to our calculation. Do you remember we started off by taking the original equation and dotting through by x? And then using the fact that x was of length 1, we ended up with this equation here. Now, instead of dotting through by x, supposing we started off by dotting by y, with a y there and a y there. We could have gone straight through the same sort of calculation, and I suggest you do this after the program. And what we would have ended up with would be beta equals y dot q, and if you calculate that, you get the answer 8. And we could have gone through the same process with a z instead of an x, and we'd have ended up with gamma equals z dot q. And that you can calculate as well. It's just 4. So in other words, we haven't had to solve any simultaneous equations at all. If we want to calculate the values of alpha, beta, and gamma, all we've got to do is to take the dot products x dot q, y dot q, and z dot q. And that's much easier than what we had before.
And what made it so simple was that the basis vectors were orthogonal. And not only that, they had length 1. In other words, we had an orthonormal basis. So, what have we done? We've looked at R2 and R3, and we've seen what we mean by a basis in each of those spaces. We've seen that in R2, we need 2 linearly independent vectors to form a basis, and in R3, we need 3 independent vectors to form a basis. We've also seen that orthogonal vectors must be independent, and that they're particularly nice ways of getting a basis. In particular, we've seen that if we choose an orthogonal basis, and especially if it's an orthonormal one, then you can calculate the linear combination of those basis vectors to get any vector in the space in a particularly simple way.